Hi everyone, I'm Tom, a data engineer from AODN. In this video I'm going to be explaining the notebook which goes through and analyzes the Seabird dataset. So there's just been a bit of an overview here. What we're going to be doing in a series of videos is connecting to the NESP 5.9 dataset, the Seabird one in particular, looking at how we can work with H3 for aggregation and mapping, and then going through how we identify different trend sites. Now, all of our NESP 5.9 datasets are summarized in this top table here. In particular, we're looking at the Seabirds though. So this is our Seabirds observation and tracking aggregator dataset. Of the datasets, the Seabird dataset is, like most of them, a singular Parquet file because it's not actually too big. The one that is distinguished here is the AMSA dataset, which is partitioned. In this section of the video, we're going to be looking at how we're going to be installing our Python packages. We recommend using UV. It's much faster than the regular pip install, but pip will work in this case as well. To familiarize yourself with the packages, we recommend having a look at the dependencies in the PyProject toml. These are all really usable, user-friendly packages, and all the documentation is online and available if you just Google it. So for our installation, say we're using the regular pip route, you do what you'd usually do. Set up a virtual environment in your directory, activate it here with this command, and finally, you would just install the packages from the PyProject toml with using the pip install dot command. Once everything is installed, you can simply run Jupyter Notebook to get into the IDE environment, and that will probably launch it on the console for you as well, ready to go. In this section, we'll be looking at the notebook stack. So for input and output, we'll be using PyArrow, which is the kind of de facto Parquet and Arrow standard library tooling within the Python ecosystem. Has exceptional performance, it's very stable, and has really good documentation as well. In particular, the FS or file system class allows us to directly connect, or establish a connection rather, with our AWS S3. This lets us connect to the data without downloading everything first. This is especially helpful for the AMSA dataset, which is a partitioned dataset. It allows us to just take the chunks we need rather than everything in one go. For computation, we're going to be using polars. Polars is super similar to pandas, it just works a little bit better with PyArrow and the Arrow standard. Has exceptional performance, greater than memory dataset manipulation, and some other fancy features as well. For mapping, we're going to be using PyDeck. PyDeck is an excellent mapping tool, but more importantly for us, where we have many polygons we need to map, is extremely fast. This allows us to keep our notebook nice and snappy. Now in this section, we're going to actually be looking at some code, so get ready for that. And in particular, we're going to be setting up the file system and connecting to the NESP 5.9 dataset. You can see here that the code we need is just the PyArrow library, as well as some of our utility functions. Firstly, we set up our file system. This establishes the connection to the correct region of AWS, so we're looking at AP Southeast True, and it also sets us up with an anonymous connection. So as this is a public data bucket, we don't need to set up any credentials or anything like that. Next, we set up the connection to the dataset itself. So we're supplying the location. For us, this is the data uplift public bucket, followed by the key of the Seabird dataset. We're passing in our file system here to let PyArrow know how to connect to the dataset and which region in particular we're looking for. Next, we're going to be listing the fragments of the dataset. For Seabirds, this is just one file, but it's useful for us, in particular for the AMSA dataset, as for previous mentioned reasons. Next, we're simply going to be printing the schema of the table. The utilities function here that we've included allows us to just quickly get the column name and the type, as well as some additional metadata commentary. If we needed to, we could use the dataset schema function itself, but we won't get a nice table and it's a little bit harder to interpret. Finally, we're going to be looking at the estimated size of the dataset. This is useful for us later when we actually download the dataset and understand if we want to load it into memory directly or if we need to do some pre-filtering or aggregation before it gets loaded from disk or delocalized AWS storage into memory. So here are our outputs. First, we can see we've just got one file fragment, and this corresponds to the path that we gave here. This is our schema table. You can see the handy column names, the type of the column, as well as additional metadata and a definition for all of our columns. Of particular note here, we have right at the bottom the H3 index, which we have added to the data. This has resolution 4, So it's been pre-indexed with H3 for every single data point at resolution 4. We've also got Australian Marine Regions tags, and we'll be going into more detail about what these are later. Finally, we can see that the estimated size in memory of our dataset is about 100 megabytes. This is small enough to fit into most computers, and we would recommend just loading this straight away as a data frame. To load the data, we simply need to use polars. Now, polars is our pandas drop-in here, which works more consistently and reliably with PyArrow, and it also has zero copy features, so we don't end up recopying in memory any of the data that we've downloaded from S3. The function is similar to pandas, where we have the data frame concept. We simply give the dataset toTable function here to directly download the data into our data frame, ready for data manipulation and computation. Lastly, we're going to do a bit of a health check on the dataset and plot some of the data over time and see how the aggregated dataset looks in terms of where the datasets are spatially and temporally. We're also going to be looking at the richness as a general indicator of how well our dataset captures all of the species in the environment. Our plotting tool of choice here is Altair, and let's just go through the code line by line quickly. We can pre-compute the x column here, as we're always going to be having the year as our independent x variable. Nextly, there's a little bit of pre-aggregation we need to do. So we're going to be aggregating by the year and keeping some of the additional information that we want to know. So for the yearly stat, we want to know how many datasets are there per year, how many records are there per year, and how many recorded organisms are there per year as well. Here we have an example of actually generating the dataset plots. So here we're calling this one dataset, but we're setting up the title. This is the dataset quantity over time. We can add our subtitle here for a little bit of additional information on our infographic. We're telling our chart that we want to be a bar chart in this piece of code here, and that we want the points plotted on as well as some interpolation to have things looking nice visually. Lastly, we just encode the channels. So the X is the X channel that we set up at the beginning, that's the years. And for this dataset, we want the number of datasets. Our tooltip gives us some mouse over options so we can see a bit of additional context when we actually explore the map itself. We have a very similar chart here for observations. All that's changed is the Y channel. Similar for quantity, where the organism quantity is plotted on the Y-axis. Lastly, we're going to be looking at richness. Now, richness is a little more complicated in terms of the aggregation that's required, but not too bad. So if we look at this, we're doing similarly an aggregation over year, as well as the data sets. And there's this subsequent aggregation here where we need to do a cumulative sum of the species and the first occurrence of those species over time. Our richness chart is also much the same, but our Y channel is richness. Finally, with this Altair vconcat, we can plot all of these in a grid and have a nice lineup of all of our x-axis attributes. So here's our grid. We can see that the dataset quantity over time fluctuates quite wildly, and that most of these initial records come from the specific Seabird log, for example, whereas later on there's different datasets which comprise the actual data and the source where it comes from. We can see that there's a loose correlation between observations over time, where these spikes here line up roughly with the trend in the number of datasets that actually comprise the aggregated dataset. Similarly, for organism quantity over time, there's a bit of a loose correlation, although less correlated than the observations. We can see that our species richness is a linear-ish trend here, perhaps indicating that we haven't seen or fully understand the entire organisms for seabirds around the Australian waters. I'll leave that up to the biologists though.